You're not going to want to miss this episode of the AI show where we talk about confidential AI. Imagine being able to safely and securely build models over sensitive data with multiple parties and strong guarantees. You're not going to want to miss it. Make sure you tune in. Hello and welcome to this special build edition of the AI show where we're talking about confidential AI. I got a special guest with me. Hello, my friend. Tell us who you are and what you do.
Hi there, my name's Sylvan Klepsch, and I'm a security and privacy researcher at Microsoft Research in the Cambridge lab over in the UK, not in Boston. And we work on a bunch of different things to do with confidential computing. And one of those is confidential AI, which I'm pretty excited about.
Fantastic. Well, why don't we dive in?
Sure, if it's all right, I've got some slides I've put together.
All right, let's go to that.
So, confidential AI is a work stream that's been going on for a while at the lab that we're pretty excited about. It's to do with the kinds of guarantees that we can offer customers in terms of confidentiality, encryption, and integrity. And it's all about data privacy and data for purpose. So when we talk about confidential computing on Azure, we already have a bunch of existing technologies that are deployed across the Azure stack for data privacy. And these are data at rest and data in transit. So we use encryption for both of these things. We use TLS connections when we communicate between servers. We use encrypted disks. We use encrypted storage. We apply a lot of technology to ensuring customers have data privacy. But what's new in confidential computing is to add the ability to protect and encrypt data during computation itself, so that while your program is running, the program itself is protected from everything else on that same machine. It's a very strong guarantee, and it's a technical guarantee rather than a process guarantee. There are lots of very trustworthy Azure services that already exist that depend on process guarantees, where a business relationship with Microsoft gives customers the confidence that Microsoft is doing the right thing in terms of protecting their data. But for some scenarios, that's not sufficient. Whether that's for regulatory reasons or ethical reasons, there are scenarios that require strong technical guarantees rather than merely process guarantees. So the platform that we've just GA'd, just went into general availability this month, is Azure Confidential Computing using Intel SGX, which is software guard extensions, which is an approach to adding a trusted execution environment to regular old Intel hardware on the CPUs that we know and love and program for. So what those look like is a little complicated. When we look at this stack, we see that in the normal operation, we have the hardware, the hypervisor, the operating system, the application, and all of these things are inside what we call the trusted computing base. And for security and privacy people, when we say trusted, we mean that is a bad thing. We mean those are the things that you have to trust. If anything goes wrong with them, your data is in danger. So what we want to do is we want to minimize that trusted computing base, make it as small as possible. And trusted execution environments allow us to get down to where we only have to trust a little bit of the hardware and a little bit of your application. And everything else, no matter how malicious it is, cannot affect your program. It can't alter its execution. It can't discover the data. There's just nothing it can do. So that isolation guarantee is hugely important. It's the secure portion of processor and memory is what gives us this trust guarantee over the chunk of code that represents the critical portion of the application.
So if I may just interrupt for a second, let me see if I'm understanding right. So what you're saying is that there's certain code, and when you say trusted, it means that it can access certain things that we don't want it to. Are we isolating that? Is that what you're saying? Because I think I misunderstood, and I want to make sure I understand correctly.
What I mean by that is the trusted code is the only code that we want to be able to touch our important data. So we want to minimize what
I
is
see.
allowed to ever touch that data. And we want to do it such that your memory is encrypted, it's integrity protected. Any attack on that computer, whether it's a hardware probe, someone with admin rights to the machine, anything like that, can't touch your data, can't read it, can't write to it, can't interfere with your computation. And that's the confidentiality guarantee.
I see. So as we're going, and sorry, because I want to make sure I understand. So basically, there's certain code that we need to trust implicitly with access to sensitive information. What we want to do is we want to make sure we isolate that code so that if it is accessing things, nothing else inside of that program can access it. Is that about right?
You got
Okay.
it. That minimizes the attack surface and makes sure that only the code that we have validated as being exactly what we want is allowed to do any operations over that data. And so when I say exactly what we want, it's one thing to say we think we're running that code on that machine, but actually what we want is cryptographic proof that we actually are running that code on the machine. What if the machine was running some other code? It's off in the cloud somewhere, obviously, so we didn't sit there physically and load it up. And trusted execution environments give us that ability too, which is pretty exciting. And this is remotely verifiable attestation. So what happens here is the hardware measures the code in the memory. And when we say measure, we mean takes a hash of it. It really is as straightforward as a one-way cryptographic hash of the code in the memory. But it's taken by the hardware. And that measurement then is signed by the hardware itself. So there's a complicated process of local attestation, which uses symmetric keys to pass a report to a quoting enclave, which has hardware provisioned public keys and can transform that report into what's called a quote. And that quote has a root of trust that carries a digital certificate that goes all the way back to Intel. That means that anyone who receives that quote without any special hardware of their own can validate that it's genuine Intel SGX hardware that's running exactly the code that we expect it to be running.
That's pretty impressive. And so basically, we're having multiple parties, Intel being one of them, saying, yeah, this is the right code because we've got the hash, and it's running in the right place because we know Intel verified it.
That's right.
Cool.
Exactly.
Cool.
So we've got that as a platform, and we want to use it for confidential AI, but just having that platform isn't enough. So one of the things that we face is a series of challenges, obviously. So a key one is that we need to redesign our machine learning products. It's not enough just to say we have some machine learning products and we have some secure hardware. We actually have to rewrite those products to take advantage of the TEE, minimize the code, have the best possible software analysis, design end-to-end secure protocols, a bunch of serious work to get this right. And at the same time, we have to mitigate what we call data leakage. So there are two different types of data leakage that pose very serious risks. One of them is model extraction and membership attacks. And these are things that can be extracted by inference queries. When someone goes and actually performs inference over your model, they can, if they have enough access to it, if they can perform enough inference queries, they can start extracting information about your model or about the training data. And the other thing is that there may be observable side channels during computation. So your memory may be encrypted, but if you access that encrypted memory in certain patterns, the attacker can do traffic analysis over those accesses to try and determine what the underlying computation really was. So there's a lot of work we have to do there. And the other part is we need to extend existing Azure services to take advantage of confidential computing. There's a lot of infrastructure in Azure, and being able to rely on it with the same kind of guarantees that we want out of our confidential AI products is an important part of the whole story.
I see. So you're saying that the first part was we have this new technology, these secure, did you call them secure enclaves? Did I get that right?
That's right. Yeah, we tend to call these TEEs enclaves. Sorry about that.
Okay, so you have these enclaves, which is just a new way of doing computation. But in order to make AI work on it and machine learning, we might have to do some tinkering with the way we do ML AI in order to work in these new hardware environments.
Exactly.
Cool.
So let me give you an example of that. Let's talk about confidential inference. So when we do inference normally, in some sense, we spin up a machine, it's running a PyTorch or a TensorFlow model, there's some load balancing HTTP server in front of it, and we send off our inference request, we run it through our model, we get a prediction, we send it back. And maybe that request is even HTTPS protected to that load balancer, but nothing else is. So the load balancer has full view of the customer data. The model, which may be a very secret model, is running on a machine that's not necessarily protected with anything stronger than the normal Azure guarantees, which, while good, are not the same thing as a trusted execution environment. So what we want to do is provide an approach that can perform that kind of inference in such a way that the model and the query data is never visible, even to Microsoft, even to people with admin access to the machine. Even if we walked up to that machine and attached a hardware probe to it, we simply wouldn't have access to any of that data. And the approach we've taken here is to concentrate on the Onyx runtime, which is an open source project from Microsoft that runs Onyx models. It's an approach to encoding your AI model. And we ported it to run inside of an Intel SGX enclave. And we did that such that we could really minimize the trusted computing base and get down to the minimal amount of code that we needed to trust in order to execute the service. So here in this diagram, you can see we have a scalable cluster, and we use ACC, Azure Confidential Computing, as our infrastructure baseline. So those are the SGX-enabled machines that are now generally available in Azure across a collection of regions. And we spin up virtual machines. And on those virtual machines, we execute Onyx inside an enclave, inside an SGX trust execution environment. And we load the encrypted model from Azure Storage into that inference enclave. And of course, in order to load that encrypted model, we need to prove that this is a true inference enclave. So we present a quote, this remote attestation, to Key Vault. And Key Vault only releases the key to that encrypted model if this really is an inference enclave that's allowed to execute that encrypted model. And at that point, we have a running inference server. But what we don't have is the ability for the front end to talk to it, because we can't have an HTTPS connection that's intercepted by the front end, because the front end can examine the client data at that point. So we actually need to develop a new cryptographic protocol, which is a tunneled stateless protocol that goes through that L7 load balancer and executes secure key export to the enclave over a shared key that can be communicated back to the inference client. So the first thing the inference client does is establish a connection to the front end and issue a request for the underlying key. That's routed to an inference enclave. The inference enclave proves to Key Vault that it has the correct code running and thus is allowed to see that shared key, sends it back to the inference client. The inference client uses that to encrypt its data and launch a second request through that front end. Now, the tricky part is with a load balancer, of course, that could go to any back end at that point. So that encryption protocol has to be stateless. And that's why we need to leverage Key Vault and secure key release in order to make this all work. Because if the second request goes to a different front end from the one that originally released the key, it'll still work. You're still going to an inference enclave that is part of the same scalable cluster and is proved that it is through remote attestation.
I see. So in this case, you're not only protecting the model because it's encrypted, but the data that's coming in from the client is also protected?
That's right, yeah.
That's amazing. That's really impressive.
Thank you. This is super exciting stuff to us. We're really keen, I have to say. Being able to offer this level of guarantee, it not just offers better privacy guarantees to existing services, it really enables services that otherwise simply wouldn't be possible, particularly, for example, in the healthcare arena, where patient confidentiality is so important that it's simply not possible to do some of these services and run some of these complicated inference approaches and algorithms without this kind of guarantee. Now, a key part of this also is that the quote from the inference enclave is also returned to the inference client. So the inference client can independently verify that it's talking to a real SGX enclave running the correct inference enclave that's loaded the correct model, such that it knows that its query is being processed by the correct backend ML.
This is really cool. I like, because one of the challenges is, like, once you build the model, if you've encrypted the model, like you said, you can put that encrypted model, you can unencrypt it and do inference, but you still have to have the client send stuff over the internet. How do you protect that? And this seems to be like a pretty impressive way of doing that.
Thank you. We're pretty excited, I have to say. So the next part of this is, while we're really excited to have a confidential inference architecture, in some sense, it only gets us so far. we also want to have the ability to train those confidential models in the first place. So let me back up a little bit before I talk about training confidential models and talk about a little bit of a different approach to building confidential software. So in the confidential inference example, we built directly on top of the trusted execution environment. We really minimize the heck out of the TCB, and we have to write a custom application that's particularly tuned to run in the enclave. But that's not always possible. Sometimes we just want to run arbitrary customer code. The customer has some huge block of Python that's running some critical part of their ML pipeline, and they need to run it in confidential mode, and saying to them, gosh, you need to rewrite that in C++ to a very complicated SDK just isn't in scope. So instead, we went down a different route. We ported the entire Linux kernel library to run inside of an enclave. Now, what that does is we take a hit. We're running a larger TCB. We're really running the entire Linux kernel inside of your enclave. So you can see that in this diagram, some of the operating system is inside of the TCB, unlike in the other one. On the other hand, what that means is your whole application can go inside of the TEE, and it can run as if it were running on a normal Linux virtual machine, and you don't have to change a thing. And this lift and shift model really changes the game in terms of what kinds of code can be run in a confidential manner. So this diagram is a little complicated. I don't mean to dive into it too heavily, but the general idea is that the key thing that you can't do from inside of an enclave is access any kind of system calls. So we need to make sure that we provide an entire system call layer, a VirtIO network backend, a VirtIO block backend. We need to handle signals, threading, time, everything from inside the enclave through a unified host interface that minimizes the attack surface. And that's open source. So we built the whole thing and open sourced it, which is pretty fun.
So let me see if I understand. When you say TC, what does TCB mean in this case?
That's the trusted computing base. That's the collection of code that might touch your data.
Got it. And then the second thing, which is interesting, is because I understood the inference bit, because I mean you're basically running very specific set of operations, and I can see how you could put an enclave around that. And so it's a little bit smaller TCB is what you were saying. But here what you did is you're basically creating a Linux kernel so it could do more things, but the trusted computing base is larger, but because of that, you actually are monitoring the host interface for any of the system calls that go through and minimizing the attack surface through the system calls that are allowed. Did I get that right?
You got it, exactly. And that gives us the ability to run arbitrary customer code. And in an ML world where most of that's Python, that really gives us the ability to run any part of your ML pipeline in a confidential mode.
Which is really cool, because one of the things that is hard to do is when you're training these algorithms, you're basically pushing a lot of data through it, which is good, but sometimes that data might be confidential. And so this allows you to protect only the code that you want to be able to train through those system calls that are protected.
That's a fantastic observation. So let's look at the next slide. That observation is the whole key to the way we've built confidential ML pipelines. So the amount of data that you got to run through these things, as you say, can be huge. And it's not always just about the training. Sometimes there's a bunch of other steps. So this is an example of a two-party confidential ML pipeline where separate entities, and let's use an example in healthcare. Let's say you have a couple of hospitals that have separate sets of patient data, and they're in completely different formats. So they want to use those two patient data sets in order to train a model to get better results. Now, the problem here is it's deeply unethical for the hospitals to share that data. But at the same time, it's also deeply unethical for them not to share the data for this specific purpose, because we could be getting better patient outcomes, and that's what we really want. Confidential ML lets us specify a technical guarantee that the data will be used only for this purpose and overcome this quandary of two unethical choices, and gives an ethical choice that allows us to train this superior model without ever revealing the data for any other purpose. And the key here is that each of these numbered boxes, 1, 2, 3, and 4, are separate confidential container runtimes, and they can run arbitrary pieces of code. So you can imagine that in boxes 1 and 2 are completely separate data preprocessing scripts. You have a completely different script in box 1 compared to box 2 because it's running over a different data set. There are different requirements for feature extraction, different munging that needs to be done, different normalization that needs to be done. But what's going to happen is, for each of those data sets, the output of that confidential pre-processing step will come up with a uniform format such that they can be sent to an aggregation container, and that's box 3, where you can run a script that understands how to perform the correct join over these two data sets. And sometimes that's a pretty straightforward union where you're just concatenating data sets. You just have two sets of data that essentially contain the same features and extend into a larger data set. But sometimes it's much more complicated. Sometimes you have an intersection. Sometimes you have data from the first party that pertains to certain kinds of features and needs to be matched to other features over the same entities from another party. Neither of these can be handled if you have a confidential container running your aggregation script. And that lets you perform arbitrarily complex data merging over confidentially pre-processed data, again, in a confidential manner, and take the output of that and go to your training container. And then your training container can be arbitrary TensorFlow, PyTorch, whatever your backend is, again running in a confidential container.
And this is impressive because, like, I've always thought about this. How do you train stuff without, like, how do you ensure that the right code is running on the right parts of the data? This makes sure that it's happening in a mathematically provable way.
Exactly. And the system not only gives you proof that each container is confidential and is remotely attestable and running the correct code, but that there's also integrity over the entire shape of the computation, so that it's not possible for a malicious attacker to run 3 over your data before 1, for example, box 3 before box 1. You want to make sure that the integrity of the shape of the computation is also maintained. Now, this is just an example, right, with 2 participants and a pretty simple pipeline of pre-processing, aggregation, and training. But you can imagine that there are scenarios with many participants and many steps in the pipeline with complicated forks and joins, but it all works. We get that same integrity guarantee no matter what the shape of the data flow pipeline is.
This is really cool. It enables multi-party model building that will enable, because like one of the biggest challenges in machine learning is that our data sometimes is garbage, and then we build models that do garbage inference because we don't have a real world aggregation of important data. And especially with social things like health, you could build amazing models if there was an aggregation of the data over all parties, for example.
Yeah, it's a really critical problem, and I'm pretty excited about this personally. I think we have a real opportunity here to expand not just our ability to produce better models, but to produce entirely new kinds of models that simply wouldn't be possible without being able to aggregate really disparate data sets.
So I love how this is all putting it together, but how does it actually run inside one of these containers? I know we might have talked about it a little bit, but I'd love to get a more in-depth look at that.
Well, let's have a look at how an individual container image executes. So here's a little diagram that tries to give a view of that. So the gray box on the outside is the virtual machine. And on that virtual machine, we have a collection of disk images, 1 through n. And these disk images, like in any Docker container, comprise the totality of the container image that we're going to execute. So that's the actual file systems that are going to get loaded. So that's your root file system, all the code you're going to run, all the data you're going to run over. Now, those get merged with the encrypted container itself and are all loaded into the confidential container image. That confidential container image is what is loaded inside of SGX-LKL. So we start up a trusted execution environment. It starts up and authenticates itself through the attestation service, gets back an attestation service, and goes out to Key Vault and says to Key Vault, I need the right keys to decrypt the encrypted container and the encrypted disk images that represent this computation. Now, in order for Key Vault to believe that this is the correct container, and that it's allowed to do that, that container has to not only prove that it's the right code, but it has the right configuration. Unfortunately, Azure's built the ability to do that. So we can get back through key release the keys we need to decrypt all of the component images and assemble the final decrypted image, but we're decrypting it only inside of the enclave. So in some sense, at that point, it's still encrypted because it's enclave code and enclave data. That decrypted container then has, let's say, your run.py. Your Python script is going to do all the work and all of the dependencies and access to all of the data and everything that you need in order to run over that collection of disk images. But as far as your code is concerned, it just sees a bunch of mounted disk images. So all it has to do is load files and munge over them just like it normally would.
This is crazy because this input disk, and I'm sorry to interrupt, these disk images that are coming in are all encrypted. And so no one can see anything that's in them until the attestation service says, yeah, this is the right thing. Key Vault says, yeah, this is the right thing. And then it runs it. And then inside of the actual confidential container runtime enclave, run.py just sees data. It doesn't care. But in reality, outside of this enclave, it's all encrypted.
Not only encrypted, but integrity checked. So the configuration of the confidential container also provides the hashes over those input disk images. And that configuration is checked during attestation and key release. So it means that your container will only run if it's the correct encrypted image that's presented to it. So no one can even fake the input data.
This is crazy town. This is really cool.
Thank you. I think it's pretty fun. Another part of it is this output disk image. So what we don't want is a situation where you have to modify your code. So we really want the customer to be able to just write out files to the disk just like they normally would. So in this case, what we do is we create an encrypted, integrity protected disk image in advance that is loaded up by an empty one that's loaded up by the confidential container and mounted. That way the user code can just write out their files like they normally would. But instead of being written out to disk in a normal way, they're actually written out in this encrypted, integrity protected image that is used for the next step in the computation. So that thing is then stored back into Azure Blob Storage with all the encryption protections, and the key to it is provisioned into Key Vault, such that the next container in the pipeline is the only thing that will ever have visibility on this ephemeral key that was provisioned into Key Vault to decrypt this image.
Yeah, and the thing about this is that, Microsoft can't look at this. There's no way for us to be able to do this without the attestation service giving the right thing to the right confidential container image and then verifying with Key Vault. And so no one can look at this. I mean, not even admins that can have all the access to blob storage at all. There's no way they can even see any of the input or output disk images.
That's exactly right. And one of the exciting things about this is this confidential computing effort reaches so deep that even the attestation service and Key Vault are running inside of trusted execution environments.
And that I didn't even realize that, because then now that is no one can go and attack Key Vault or the attestation service.
That's right.
This is pretty cool. So what else do you have? Was this the last? Because I feel like I've got a really good picture of what's going on.
Thank you. This is pretty much it. This is the deck I wanted to present and the stuff I wanted to talk through with you.
Well, this is all really amazing stuff. Where can people go to find out more?
Please have a look at the Microsoft Research Cambridge website, particularly the Confidential Computing Theme Group. We have a bunch of information on confidential AI and a bunch of the other confidential computing efforts we've put together. And there's nothing we like more than sharing it and talking about it. So please have a look.
Fantastic. Well, this has been amazing. Friends, we've been learning all about confidential AI with strong, to me, it's really impressive that this is able to be done. I'm so happy that you were able to be with us. Thank you for watching, and we'll see you next time. Take care.